An Enhydro quartz crystal can look like a sealed time capsule. Hold it against a steady light, tilt it slowly, and a dark bubble may glide through a clear pocket inside the stone. That movement is real evidence. But it does not prove the liquid is ancient, untouched, or even water. And if you crack the crystal to find out, you may destroy the only evidence that could have answered the question. So before anything else, leave the specimen exactly as you found it. Do not shake it, heat it, freeze it, soak it, or tap near the cavity. Place the crystal on a stable surface, photograph the face pointing upward, and mark that orientation. Every later movement needs a reference, because the first question is not how old the liquid is. The first question is whether the moving feature is truly inside the stone. Put the crystal in front of a steady backlight and move the specimen, not the lamp. Tilt it through several angles while watching one suspected cavity. A gas bubble inside liquid should respond to gravity, while the boundary around it stays fixed. In a broad cavity, the bubble may rise freely. In a narrow channel, it may hesitate, stretch, or lag behind your hand. Now reverse the tilt. If the dark bubble returns to the high side, while the cavity wall remains in the same place, the case for an internal liquid and gas pocket becomes stronger. Bring the crystal back to the photograph's starting position and repeat the movement. A repeatable path matters, because random reflections and surface moisture do not usually behave like a gas phase trapped inside a fixed cavity. That is the first useful payoff. You are probably not watching a loose drop of water roll through empty quartz. The cavity appears to contain fluid, and the moving shape is usually the gas or vapor phase traveling through it. Together, the liquid and bubble form a two-phase fluid inclusion, but a moving bubble is evidence, not a certificate. A droplet on the surface can slide. Polishing compound can collect inside a pit. Adhesive can sit inside a repaired seam. A scratch or open fracture can look buried when the light hits it from the right angle. This is why the next test uses focus, side light, and parallax instead of force. Hold a loop over the suspected cavity. Focus first on the crystal surface, then slowly focus deeper into the stone. An internal feature should remain below the polished or natural face as the focal plane changes. Shift your eye slightly from side to side as well. Material sitting on the surface will move against the background differently from a feature buried inside the quartz. That apparent shift is parallax, and it helps expose the easiest false positives without damaging the specimen. Then trace the entire visible boundary. Look for an open pit, a seam reaching the outside, or a fracture that continues from the cavity to an exterior face. Cloudy quartz may hide part of the root, so turn the crystal slowly and examine the same edge from several directions. Finding a possible root does not tell you when fluid entered. It changes the immediate decision. A pathway to the exterior makes perfect long-term sealing less convincing, and it makes drilling or cutting even harder to justify. Time gives you one more non-destructive check. Return to the original photograph after time has passed. Match the same orientation, use similar lighting, and avoid a major temperature difference. Compare the bubble size, the apparent liquid level, and the cavity boundary. A persistent change may indicate leakage or an open pathway, although temperature can also change the relative volume of liquid and gas. Record the change instead of forcing an explanation. The photograph cannot date the fluid, but it can warn you that the cavity may not be stable. At this point, you may have strong visual support for an internal multiphase cavity. What you still do not know is when that fluid arrived. The cavity wall is the next clue. Turn the quartz until the edges catch the light. Rough, irregular walls may remain ambiguous. Flat faces and sharp angles can mirror the geometry of the surrounding crystal. Gemologists call that crystal-shaped void a negative crystal. If fluid became trapped while the quartz was growing, the inclusion is primary. Fluid at depth can be warm and can hold dissolved gas. As the crystal and liquid cool, a separate gas or vapor bubble can form inside the sealed cavity. The Gemological Institute of America has examined Moroccan amethyst with large primary inclusions and freely moving bubbles, including examples visible without magnification. The geometry supports a formation story, but it still does not deliver a date. A crystal-shaped cavity can be old, yet the stone around it may contain evidence of later events. Look beside the cavity for a pale healed line, a fingerprint-shaped trail, or a fracture crossing the field of view. Quartz can crack after the main crystal has already formed. Fluid can enter that fracture, and the break can later heal around tiny trapped pockets. Those are secondary inclusions, which means the fluid is younger than the original host crystal. Some quartz specimens have contained primary and secondary inclusions together. That matters because the age of the crystal and the age of the trapped fluid are not automatically the same. Your loupe may show both histories in one piece of stone, but it cannot assign a calendar date to either one. The clear liquid also does not identify itself by appearance. It may contain water, dissolved salts, carbon dioxide, hydrocarbons, or other components. A visible bubble supports more than one physical phase inside the cavity. It does not provide a chemical label. Host material creates another major fork. Clear crystalline quartz can contain a small cavity enclosed within one larger crystal structure. Chalcedony and agate are different. They are built from masses of extremely small quartz crystals, creating a microcrystalline texture around a larger hollow space. Gemologists usually use the word enhydro for a hollow chalcedony nodule or geode that contains liquid, although sellers also use enhydro quartz for clear quartz with a visible fluid cavity. The distinction matters because chalcedony can be slightly porous. Over long periods, fluid may move into or out of an agate cavity. That means a genuine moving liquid level inside agate does not prove the cavity has remained perfectly sealed since the stone formed. Scishow raised this exact caution while examining claims about Brazilian enhydro agates. The cavity may be natural and interesting, while the claim of pristine ancient water remains unproved. If you collect quartz, agate, or unusual mineral inclusions and want more evidence-first checks that protect the specimen instead of feeding the myth, subscribe. The next part is where curiosity turns into irreversible damage. The water jet channel opened a Brazilian specimen to reach the liquid inside. The process looked direct. Drill into the cavity, expose the fluid, taste it, place some on culture media, and cut the stone open for a better look. But the moment the drill broke through the cavity wall, the original system was gone. Internal pressure was released. The liquid touched the drill bit and outside air. Material from the tool, hands, surface, and surrounding environment could enter. Some fluid could evaporate. The cavity wall that might have helped explain how the pocket formed was now broken by the very action meant to investigate it. Before drilling, the bubble, liquid, cavity boundary, fractures, and host existed as one intact relationship. After drilling, every observation carried the disturbance with it. Reaching the liquid did not make the specimen easier to interpret. It made original evidence harder to separate from contamination and damage. Sawing the stone pushed that loss further. The cut destroyed more of the relationship between the bubble, the fluid, the fracture pattern, and the surrounding mineral. Polishing toward a cavity can improve visibility in some commercial specimens, but the remaining wall may be extremely thin. The available evidence provides no universal safe cutting depth. Bacteria reported from drilled Brazilian agates resembled organisms associated with tropical surface soils. But chalcedony porosity, the drill, the operator's hands, open air, and the exposed cavity all complicate contamination. Tasting the liquid or watching growth on an improvised culture plate cannot establish its age, safety, origin, or evidence of ancient life. The fastest route to the liquid is also the fastest route to losing its context. Heat and freezing create a similar problem. Temperature changes can alter the relative volume and behavior of the phases inside a cavity, and extreme treatment may damage the specimen. Repeated wetting can confuse surface observations. Scratching, striking, or drilling near the inclusion risks destroying the feature. Unknown mineral fluid is not food or drink, so tasting has no place in the examination. When the bubble behaves consistently, the boundary appears internal, and no exterior route is visible, you have reached the ceiling of home observation. You may have strong support for an internal multi-phase cavity. You still do not have a verified age, chemistry, locality, treatment history, natural origin, or market value. That is where professional examination becomes useful. Qualified gemologist or mineralogist can use microscopy to map growth structures, healed fractures, and cavity relationships more clearly than a hand loupe. Depending on the specimen and the question, spectroscopy, petrography, and controlled laboratory analysis may help identify the host, the material inside, or the conditions under which the inclusion formed. None of those methods guarantees a precise age, and none should be copied as a home heating, cooling, drilling, or chemical experiment. Collector value follows the same logic. A clear, well-positioned moving bubble may make a specimen more desirable, but there is no honest fixed multiplier. Crack the cavity, and you can lose both the scientific evidence and the exact feature a collector wanted. So use a simple decision order. Keep the specimen intact when the moving cavity is stable and defines the stone. Continue with non-destructive professional testing when authenticity, composition, age, provenance, scientific interest, or sale value matters. Stop when the next action would release fluid, alter pressure, break the wall, or introduce contamination. Return to the steady light and tilt the Enhydro quartz once more. The moving bubble still catches your eye, but now it marks the boundary between observation and proof. It may preserve ancient formation fluid, or it may record a younger event. Photograph first, tilt slowly, and protect the cavity. If cracking the crystal erases the answer, cracking is not the first test.